Okay, we've arrived at our last lecture, Module 6. This 1 week module has 2 lectures. And we'll have again one quiz right after this one, where you do a couple of examples, respond to a couple of questions, and then there will be this optional assignment to do at the end. So let's think about where we just finished, looking at parametric programming. And one of the examples of that is actually related to risk. Okay, so one of the conundrums or problems that a optimization modeler faces when dealing with risk problems is they either need to know someone's risk attitude, or they need a way to find the trade-off, or they need to pick among mean or variance. Which is more important? Because we need that single valued objective. Okay, and so the approach we took was, let's use the model that describes choices under risk. This was during residency, to find the efficient mean variance frontier. And that was a parametric program because we were finding the lowest variance option that gave us a target return. And so we adopted the target return, we increased it by intervals, measured the lowest variance, and then we had a set of plans that guaranteed the lowest possible variance for each return. And so though we could say those were efficient, and that gives us a place to go forward from in doing our analysis and thinking about risk. It tends to be much bigger than, the tolerance for risk in a project, or even in a mixture of projects that work like a portfolio problem, tends to be bigger than just the decision on the sort of isolated decision on a short-run plan. And so it may depend on the cash position and some other sort of performance measures on what, during any sort of plan updating situation, the firm is facing, what the current sort of risk tolerance is. And so that's sort of what we did, and we went through and did our mean variance residency, where we took that portfolio type mean variance or portfolio type covariance among choices, subject to meeting those minimum return guarantees, and we plotted that function and saw what it looked like. Other approaches to risk, and by far, the sort of dominant measure, is for idiosyncratic responses. So if you were to go out and build models over and over and over for every firm, and then look at firm information, look at firm choices, you might find that very few of them are on the mean variance frontier, doing the efficient outcome. And and there's a reason for that. It's not, these are all sort of abstractions, but most firms actually have sort of a internal design, a threshold sort of approach. When A happens, we switch to this sort of riskier plan, right? If there's a forecast that comes in and says that there's some option here, or something that unrelated in the market outcomes happens, right? So you end up with these sort of tiered, threshold-driven behaviors that don't actually produce mean variance efficient returns, but they may not be defining risk in terms of just the portfolio variance. That is a specific definition of variance dedicated to that internal portfolio of actions, when in fact there may be covariance among all of these actions in the portfolio with some other behavior in the firm, and that has to be accounted for. And it makes it difficult to make any sort of claims about whether a firm is efficient in terms of their risky behavior. Plus, there's always the fact that the risk attitudes change enough across firms that it would be difficult to understand. So the sort of second literature on risk really comes from a game theory side. It says, what are sort of strategies that a firm might play in a game, right? So you take this, they call it game theory because the setup is there's a decision maker and there's nature. Okay, nature is out there and it plays some state, some outcome happens. You don't have control over it and you don't know it ahead of time. But you do know all of the possible states of nature that nature might play against you. So nature plays that state, you've already committed to some activity or to some strategy, and you get your outcome. And so you backing away from that, how would you look at the possible states of nature that are in play that can actually occur and make choices? And so we look at one of the most common, but the idea being you could extrapolate from the analysis, this parametric programming approach we're going to take to this, or this kind of setup, and you could work forward from it using any sort of decision model that incorporated firm-specific strategies and thresholds on decision making, right? Do you switch to, what kind of projects or what kind of productivity levels are triggered? I mean, do we make more cars when there's something happens in the oil market, or do we make more of a certain size of car, right? Do we up those production lines versus others? And those are all sort of responses to uncertainty that we might be able to sort of build into a decision model, and also sort of track multiple sort of response functions in those. Okay, so clearly, if we're going to teach this stuff, we have to adopt one that isn't specific to a firm. And so one of the most common that tends to fit a lot of price-taking producers, which is sort of a classic agricultural assumption, is the maxi-min criterion. It's sort of a two-stage game, response play. The idea being, first round you go out and look at all the possible states of nature that could occur this year, and then narrow your focus to only the worst outcome for every state of nature, for every decision you can make. So if I have option A, planting corn after corn, and there are 3 possible sort of weather forecasts that might determine yield and have a price that corresponds to those so that I have a revenue outcome, then my goal would be for corn after corn, what is the worst outcome I could face? And then if I had some kind of wheat following corn, or double crop, wheat and then beans that followed corn, look at the worst outcome across the states of nature that could happen there. And then, whatever else there is, some tomatoes, whatever it could be. So looking at all of my options, isolating each option I have and looking at states of nature. Once I've gone through and found for every action I can take, what is the worst possible outcome, assuming nature plays me the worst possible choice, gives me the worst possible state of nature, I'm left with only a row of my choices and the worst case scenario under each choice. Then the second round says, okay, you've identified all the worst case scenarios for every action you can make, now pick the best one. So you've zeroed in on risk as, I assume the worst case scenario will happen no matter what I do. What is the best I can do among the worst case scenarios? And that's how the problem plays out. It sounds more complicated explaining it without any numbers than it does with, so there's always a small example like this. And here we have it. So we have the game set up as the farm decision maker on this side, the nature player up here. Nature can play state 1, state 2, state 3, and the farm can play action 1 versus action 2. Okay, and so the farm's choice. For a maxi-min farm decision maker, you look at X1 in isolation, find the worst possible scenario, which is state 2, and that's the one we're going to focus on. Then move down to our second possible action, across all of the states of nature, find the worst possible case, and that's the one to focus on. So we have it down here, farm X1, S2, state of nature S2, worst outcome is 40, when under plan X2, state 3 is the worst outcome and earns 30. Comparison of those, we maximize among those two, or among the circled items here. So farm plan X1 earns the maximum among the minimums. That's where you get the maxi-min. And that's efficient for a maxi-min decision maker. Maxi-min can be written, maxi-min is obviously a pretty conservative approach to risk. It is just narrowly focused on the worst possible outcomes when you know, we don't have probabilities up here, but if this is a low probability outcome, a maxi-min sort of plays for that low outcome. Then obviously you can make alterations when you had a guess at what the probabilities were, if you have forecasts that update these, but those aren't built into the rule the way we've done it here. Anything else would be an expected value decision maker, right? And so the nice thing about maxi-min as a decision rule is we can write it up in a spreadsheet model as a linear program. It's not obvious how it works, but we'll demonstrate it here, and you can pick it apart as well for your quiz. And then obviously if you do the optimization problem, you'll have to play with it more. Okay, so it may be the case, right, if you were dealing with a firm that had a much more intricate, we want to look at the average of the 3 possible worst years or states of nature or whatever, then you'd have to adopt some sort of mixed criteria. But you could do all that in a spreadsheet, right? And as long as you are consistent with the constraint, consistent with any weighted averaging that needed to be done using the expected probabilities, you could do any of this analysis that we're talking about here, where you set a target income level and see how much risk you're taking on and see how the choices that you're going to make change. The parametric programming summation of our risk response. So the big catch here is T. T are the years that we've collected returns data on historically. Okay, and so you see a T pops up right here. So these are going to be, instead of saying give me the average return over the last 10 years, I'm going to use those as my collection of states of nature. They've happened in the past, they could happen again. And so in this case, we're replacing states of nature with observed past outcomes. Okay, so CJT is some past return per acre of a crop, for instance. XJ then would be the choice we can make now, and then M is the maxi-min expected return. It is the best among the worst outcomes. Okay, and so what this is saying is go through the history of outcomes that have been observed, make XJ a choice variable, a non-negative choice variable you see down here, and make it fit with the technology constraints or the resource constraints of the firm here. And then M is going to be a selected variable. It's going to be a choice variable that the model is allowed to adjust, and it's going to adjust it in a way that forces it to be the largest of the worst case scenarios. Okay, that's what this setup does. It allows M to be a choice variable, so I think the spreadsheet requires you multiply the choice variable times 1. It may not anymore, but at least the setup that I learned did. And so they've written it here as the same thing, but anyway, you're choosing M to be as large as possible with the idea that it sits on the right hand side of this constraint, and so you're going to track over all this historical data and push M up as large as possible while still only while restricting yourself to the worst outcomes that are in that historical record. So let's look at our problem. Let's convert this problem right here, state 1, state 2, state 3, versus these choices to a spreadsheet model type setup. So we have 3 choice variables here, the X1 choice, the X2 choice, and M, which starts at 0 as well. The objective over here has a coefficient of 1 times M, and so that's what you'll see in that cell when we open the spreadsheet. The risk constraints are state 1, state 2, and state 3, and those are just the historical measures, or the state-based measures, right? So state 1 earns 100, state 2 40, and state 3 80 for choice X1. For X2 it's 50, 60, and 30. And so this is an easy problem to solve, right? You just track through this column, you pick the 40, you pick the 30, and then the best of those two is 40, and so M had better be 40 when we solve this. Well, if you tried that without this activity allocation constraint, you would find that the problem can't solve because it can make M as large as it wants. It can never find a converging solution. Is probably the better way to state that. And so you have to force the problem into a choice. There has to be a condition that it has to meet. And so 1 times x1 plus 1 times x2 has to sum up to 1. So you have to commit to one or the other. Okay. The objective is M. It's a non-negative choice variable. The first constraint is that total allocation, right? So you're going to have to commit to one of these strategies. And then the state constraints basically say that for feasibility, you're going to find M to be as large as possible while meeting any feasibility conditions and also selecting among the worst outcomes. Okay, so I think we're ready to look at the spreadsheet for this. Okay, you have this spreadsheet in your workbook for this week, LEC 6.2. The same setup we just looked at, and it's our same setup for every LP we've had. It's really just, you see here we have the sum product of the 3 choices times what we have here. These constraint coefficients, right? This is like having M on the right hand side over here, but we have it on the left hand side times -1 coefficient. Sum products all the way down, and then I told you this would just be this times 1. I don't think you have to do that though. And then we just set up solver, and I think when you open this it'll be set already. Let me take that part out. Okay, so we're going to maximize G2, the objective cell. It is a maximization, and we got to change all 3, x1, x2, and M. That's the important part. Subject to the constraints, so the first one actually I've used as an equality here rather than greater than or equal to, so I'll fix that before I post your spreadsheet. And then the second one are just the greater than or equal to constraints. So let me so if we run that, we should get something, and it doesn't look great for us. It's saying we should do, okay, so it found a solution, the constraints and optimality, etc. is all good. And let's keep that solution for a second and look at what it did. It says, well, the maxi-min is 51, and it's a blend of 43% of x1, 58%, 57% of x2. Now, we have to ask ourselves, is that the intention of someone who wrote this model and said, choose plan x1 versus x2? It probably isn't, and so that's why you saw I had integer constraints, because we're going to fix that in a second. But if we had a crop model that had 4 crops in it, like our problem you're going to see through your assignment if you do it, x1, x2, x3, and x4, let me just zero those back out. And these were the historical returns for the crop. And we wanted to sort of come up with crop mixes, given these being, this is the 6-year tracking of returns on the first crop. Here's the 6-year sort of per acre returns on the second. Well, that's a case where we would want to let it blend. We want to let it look, and the entire point of this LP setup, right, where you choose M to be the right hand side value, right? So 1 times these, or whatever the value of M is, times these, has to be such that you find the M that is large enough to cover all of these constraints, and that means it is bigger, it is largest among the worst outcomes. So when you get a binding constraint down here, it means it is one of the worst outcomes. It is part of the collection of worst outcomes. When you get one that's surplus constraint, it is too large. It is too large to be considered. It is bigger than the smallest outcome, than the worst case scenario. And so here we have it. We could have guessed that 150, right? It's better than the worst outcome here, better than the worst outcome here. And so that's why it shows up with slack if we were to take care of that. Those go to 0 and they're binding. But these are binding because they form part of the worst linear combination, the worst set of combinations that include worst case scenarios. Okay, and so what this is doing is saying if you can blend x1 and x2, then the maxi-min choice is actually about, I don't know, 43% and 57%. Mix it up. But that's not the solution we wanted to check. We wanted to see if we could get this to show up as 40. And so it turns out the only thing we need to add to that is, do you remember how to do integer constraints? You do it through here. You go to add, and then x1 and x2 are the only things we're going to force to be integers. And we just select I and t, and you click OK, and you click solve. And there we have it. It said, let's pick through here, and let's find the binding constraint is right here. And it is also the one that contains the best worst outcome. Okay, these have surplus. That's because they are not part of the best worst outcome when you're forced to choose either one of these two actions, right? So these are discrete actions, x1 versus x2. Okay, so it's getting close to the end here. You'll have a quiz that lets you play with a different version of this. That follows this lecture, but if you move on into the assignment, then you'll have, even if you don't move into the assignment but find yourself needing to do this someday, you'll have the assignment that you can use as a guide. What do you do if you have this extra data? So this is the extra data that you'll use for mean variance analysis in the assignment, and we'll compare mean variance. That assignment will compare mean variance to maxi-min outcomes and look at different the different approaches to risk in those two options, those two criteria. This is the LP setup you would use. It looks exactly like what we just had. The risk rows are these outcomes that are historical for the 4 different crops. This is the land requirements. So we have a physical limitations on production. Same with labor. We have those requirements. And then there's this additional rotation requirement that says X1 and X3 are rotation crops, and they you have to balance those out with X2 and X4. Okay, there's this one last sort of piece of this model, and it's the expected total gross margin. So one of the things about maxi-min is it's a little, you solve it and you get the maxi-min outcome. Some analysts said, well, people aren't really maxi-min decision makers, but lots of people behave that way, except for the fact that they have to cover costs somehow. So they have to give the firm a chance of covering costs. And so what they've done is built this as a parametric program and said, here are the expected returns for each of the 4. And so multiplying these 4 together times the activity levels gives you a minimum return. And so it's just like the mean variance problem, where we are going to, in the assignment, come up with a set of minimum returns that we have to hit as part of the feasibility. Okay, and so if we set this first at 60,000, then at 62,500, and then at 65,000, you'll see the mix changing as we require more and more more and more expected income. But if we're driving up the expected income, we expect the risk to increase, and that would be captured by a lower maxi-min criterion, so function. Okay, so you'll find that as you drive this higher, you are having to take on more and more of the not best among the worst outcomes. You're having to take on more of that variability that you were trying so hard to avoid. Those worst outcomes are getting more and more play. And so here's what an initial solution to that problem looks like. So you have the optional reading that goes with the assignment this week is from Hazel and Norton. Here's the expected gross margin set at 0, so no criterion on it. And the maximin function generates to 60,000. The expected return is higher than that, 65,000. And so one measure here that is of interest is how big is the difference between the expected return and the maximin return, because being very small makes it a very, the maximin return is measuring the largest of the worst case outcomes, right? And so the gap between the expected return and this is a measure of predictability, right? So we have a very certain level of income here, given these being the states of nature that have been observed. And so the gap here is a measure of risk that we're taking on. And so there's some upside here, but we're cutting off a lot of the upside as well in this problem. So this is our expected return. All the constraints are the same, and then here we see down here there's 4 binding constraints. And if you track through here, you'll see the worst outcome for option 4, the worst outcome for, oh, sorry, not the worst outcome, the worst outcome here, the worst outcome here. Now you can't get all of those in there because these are combinations across the 4, but these dominant, very low 5, negative 128, and even here 114 tend to cause those to be part of the worst set of combinations that you can come up with. Okay, with that you have a little quiz on maxi-min as a criterion, and then of course the assignment has a little bit of reading, a little bit of reference to that Hazel and Norton chapter, and a lot of sort of steps that you can play with in your spreadsheet model. The spreadsheet models I give you to look at this and to try to come up with ways to compare mean variance versus maxi-min.